Thank you all for coming. So my name's Dharhas Pothina. I'm the Director of Consulting at QuantSight, who was sponsoring the conference. And who here is from astronomy? Anyone? Oh, come on, there's got to be someone. Yeah, physics. I don't know. So I was a little worried because most of the people in data science seem to end up coming from somewhere else. And I'm not an astronomer. I basically know stars are big balls of hydrogen, kind of, things like that. This is a talk which is partly based on astronomy. And Tim Morton, who is at University of South California, previously at Princeton, he's the subject matter expert. This is kind of a good example of scientists, commercial company, and the open source community working together to build something which I think is pretty cool. And so I had not heard of the LSST before this project, but it is a telescope being built in Chile that's going to go online in 2022. That's what the construction currently looks like. It's not fully complete. The mirror and other stuff has been constructed. I think it's already been, the mirror's already been shipped to Chile, and they're doing integration. The website's pretty cool. I'm going to show you a few more pictures. It's, from my understanding, so the bottom picture is actually the size of the mirror, and it's the largest telescope mirror ever built, and it is going to survey the entire night sky every couple of days for 10 years, like depending on cloud cover and stuff. Expected to generate 15 terabytes of data a night, 60 to 100 petabytes over the 10-year period. Okay? When business people keep talking about big data, they haven't really talked to astronomers, or my original background is computational fluid dynamics, hurricane modeling, all that kind of stuff. We deal with data sets which is a lot bigger than most people who are talking about Hadoop and all that kind of stuff. So what's the problem? Okay, this is a lot of data, okay? And so they've actually have a whole team. So this is not going to actually be turned on till 2022. But there's a whole team of multiple scientists and engineers and stuff. There's a whole corporation behind this, and they're building the data. There's a whole team building a data pipeline, because this is in Chile. The data has to come back to the US, be stored somewhere, transformed, cleaned, everything archived, and so there's a whole group building a really complex data pipeline. Guess how they evaluate whether the pipeline's working correctly? Any guesses? Who's? See, I'm going to put the next little bit up. I'm going to talk about it a little, because we've all done this. This is how they evaluate the data pipeline. They got a folder full of static plots, and someone's kind of flipping through them. Saying, oh, that one looks bad. Let's go back and rerun. And I'm joking about this a little because I've done this, and I'm not hitting on Matplotlib, because Matplotlib was my gateway drug that pulled me into Python in 2008, because I was using MATLAB and I found Matplotlib and everything was lovely. So I love Matplotlib. It's a great tool for publication quality, print graphics, and things like that. It's not a great tool for this problem. So Tim kind of talked with us, and we're like, okay, we've got a better way of doing this now. And the way we're doing this now isn't something that was possible even a couple of years ago. And what does the LSST need? They want an open source stack. They're a scientific engineering group. They want to be able to mess with the stuff. They don't want something prepackaged that they can't change. It's got to be interactive, because they're trying to understand why things are broken, in the data pipeline and stuff like that. It's got to handle large data sets. I mean, it has to handle large data sets. If they can only see a tiny piece of their data, it's useless for evaluating their system. And it's a science organization. They cannot afford to have an outside organization maintain their stack. They have to be able to tweak it. And there's two parts of this. And this is a little picture I put below. If you go to the HoloViz webpage, because some of the technology we're using come from HoloViz, there's a really nice example of the New York taxi data set and visualizing it in the browser and kind of playing around with it and stuff. And so that's what we usually do. We play, as scientists, engineers, we play around stuff, build plots, things like that. There's another website I call it, this is Hubcap, I kind of found it a couple of years ago. It's a really slick interface to explore the same New York taxi cab database. And it looks amazing, and it works really well, it's great. But it's a custom coded app built by a team of JavaScript developers. And when you know exactly what you want, you can throw resources at building it. Do you have a question?
So is what they're looking for still going to be something where the tests are signed off on by like an actual human person, or are they looking to do something more automated?
No, so they're building so they have raw sensors that collect the actual data in different wavelengths, and it goes through a pipeline of processing steps before they have the data sets that the scientists are going to use. So they're building that data pipeline, and it's an automated pipeline, but they need to...
Automated testing. Is it going to have automated testing?
Yes, so one of the things with the dashboard I'm showing you, which isn't done yet, is they want to have, so they've got some metrics on the things, and they want to have some pass-fails on those metrics, and when the metrics fail, they want to explore the data on it. So the dashboard is meant to show those, which metrics have failed so they can explore them. So yeah. This cycle, so the dashboard on your right, when you know what you need, building a really polished app for that is easy. You throw money at it, you throw developers at it. The problem is you often don't know what you need. And the people who have the domain expertise to build and experiment and try and work out what you need, they can do this. They can't write JavaScript. They don't want to write JavaScript. I've been in organizations where going from this to that is a 6-month to 1-year process with a separate team where you're trying to educate the JavaScript people what the science. Actually, this is an anecdote from a long time ago. I was working with a group of web developers, and we were building a website to show all the hurricanes that ever hit Texas. And this was back like jQuery days, like 10 years ago, and they said they could only display 200 hurricanes at a time. I'm like, okay, that's fine, we'll work around it. But they decided to, every time you refresh the page, it would show you a random 200 hurricanes. Not the alphabetical, not the year. And I was like, why would you think that would, but for them it was a computer science problem. It wasn't how will people use this. And so that's the problem you have when you have to throw something over the wall. And I call it the scaling problem, and this happens in a lot of different areas. You know, conceptual model, high fidelity physics, Python to JavaScript, Java. When you have to change your tool set or toolkit as you scale, you have impotence, you have problems. And often you hit a cliff. So yes, I can do my stuff in a Jupyter notebook, I can do it on one computer. Oh, my data set's too big to fit in memory. Oh, I need to go write everything in MPI. Or I need to, you know, so it's this kind of thing where your experimentation and your place where you experiment and the place where you do things at scale are completely different and have different toolkits, different skill sets, different people. And that slows down innovation, and it slows down your ability to communicate data and communicate results. So we built this on an open stack. And I'm going to not go into detail about this, just kind of give you the pieces. Dask, you've heard a couple of talks about Dask. Dask lets us scale to bigger and bigger data sets while still being in a pandas, NumPy-like interface. So it feels the same even though you're using bigger data sets. HoloViews lets you really easily build interactive linked plots where what you do on one plot is connected to another one, and you can explore and you can search. Datashader is my favorite thing ever. I met Jim Bednar a couple of years ago, and he presented a SciPy and Data Shader. Data Shader lets you now, what it essentially does is, if you have a really massive data set, let's say it has 1 billion points. If you are looking at it on a browser window, and you push that 1 billion points to the browser window, you will crash your browser. But you can actually only physically see 800 pixels by 800 pixels or whatever. So Data Shader intelligently rasterizes your code, your data, so all that you're sending to the browser is one image. And as you zoom and you pan and you do everything, it re-rasterizes it. So it doesn't really matter what the size of your data is. You can always interactively manipulate it in a browser interface. And then this is all really good for experimentation. And Panel now lets you build the app or the dashboard that you want to deploy to your users. We want to prototype in Jupyter. And we're kind of experimenting with deploying with Jupyter Hub on their cluster. And that's still kind of happening. But this stack allows scientists and engineers to experiment and push things along, but also to deploy apps at a good scale. It may not be as polished of a end product as a 5-man JavaScript team writing everything in D3 over 6 months, but I guarantee you can iterate much faster. And if you do come out with, oh, this is the exact analysis we want, then it may be worth rewriting it directly in another stack. But this lets you experiment. And the rest of my time will be a live demo with code that is not completely stable. So we will see how this goes.
You can do it, Dharhas.
Yeah. So there's two pieces of this. There's a bunch of data engineering, and all this code's online. I'll share it later. But I'm just importing. We wrote a little module called LSST dashboard. It's not that much code. There's one dataset.py file that handles getting the data out of their system. And there's a GUI.py that implements the dashboard. And I think it's maybe like 150 lines. It's not a lot of code. And OK, the one fun thing, I asked when we started this project, I asked Tim, OK, I need a small test data set just so we can experiment. And he gave me 0.5 terabyte. So this is 10% of that data, just because if I need the full data set, I need to be on the cluster, and I didn't know how Wi-Fi was here. So I'm using 10% of the test data set right now. And I've got it locally instead of on the cluster. So I'm just reading it in. This is just a little class that reads it in, connects to the data, kind of does some reformatting, pulling in different data sets. And right now I'm reading one tract. So they divide the sky into tracts, which is like one piece of the sky. And the test data set is 3 tracks. I think I'd have to talk to Tim. I think it's like several hundred tracks is the entire sky. And we have these filters. These are, from what I understand, these are different wavelengths of the light. They've got different sensors for the different wavelengths. And for each wavelength, and they have this concept called explaining there's a whole thing of me understanding the domain of this data. So every time the telescope tracks a particular area, that's a visit to that area. And then they aggregate multiple visits into a compiled data set called a tract. So, and for each of that, they have about 300 variables. And these 10 or so variables are metrics that talk about the data quality. And I have no idea what any of these words mean. If you're from astrophysics, it might make sense to you. This is what they want to look at to decide whether the data pipelines is good or bad. And they want to write some kind of conditions. If this one varies by a certain standard deviation, then mark this, this metric failed or something like that. Now, if I pull out one of them, I'm going to pull out this HSG cron PSF magdiff MMag, which I have no idea what it is. This is a DASC data frame. So it took about a second to pull that out. If you see, there is actually no data here. All it says is there's 3 partitions. So, and this is a small data set. There's only 3 partitions. So it's just a placeholder with kind of pointers to where the data is, in some sense. And if I do here I'm going to do a df.compute, and it's going to kind of aggregate everything and give you back a pandas data frame. This worked right now, and if you see at the end, you got some data, and then at the end, they ran a classifier on it, so it tells if it's a galaxy or a star or something they didn't recognize. If I did this df compute on the actual data set, I'd crash my browser or my Jupyter because, half a terabyte browsers, do the math, But usually what happens is, usually in the system you wouldn't do a df compute. Dask will let you lazily kind of pile things on. So you see the length of this. This is 1.3 million, 1.4 million rows, and I do a filter and some stuff, and I get down to a smaller thing. So you'd probably run some filters, and so I'm not. There's nothing. So the point I'm making, like this, I'm going to take some of those data sets. I've got a data set and a filtered data set, and I'm just going to use panel to say I want a column and 2 rows with the data and the filtered data. And now I have a nice little plot which shows data, filtered data, something else. So this RA and dec, that is right acclension and declination. So that's kind of a coordinate system of where you are, longitude and latitude. And this is some metric here. So the point is, these are the kind of plots scientists will make and are comfortable making in Jupyter notebooks. We're using some fancy tools, but it's not anything too difficult for someone who's reasonably good at scripting and Python to learn. Now, I told you we have about 150 lines of code, maybe 200 lines of code in this GUI.py. And I'm going to import that. And now I can say dashboard.render.show. And it launches our full app. I'm actually going to close it. I just wanted to show you could launch it from Jupyter. But I'm going to run it another way because we also want to be able to do this as a deployed website. So let me close this and restart this. So we have this panel serve command, which basically takes your entire application you've built and just serves it as a standalone website. And so that's, and right now it's running localhost, but we could run it as an actual website. And there you go. And let me get the folder name. OK, so if I was running this on the actual cluster, the path I give there would actually communicate with, they have a software called Butler that works out where this data is on their archive system and returns the data sets to you. But right now I'm just giving it a folder on my local directory. And it's going to read that data in, and then it's going to populate what's available over here. And so that's what's available. And I'm going to just pick something. And let's see. I will pick this. And so this is one of the filters. And you can see it. Or I could turn it off. Let me go here and pick this. OK, so this is some data. And this is, as we saw, about 1.5 million points. If this is 1/10 of the data. This also works on the full test data set, which is 10 times larger than this. But now I've got all my interactivity. I can zoom around. It re-rasterizes as I'm zooming and panning. So if I zoom out, it will work out the correct scale to use and what colors map to use there. And this is, I can inspect a particular area. And I can look at that, and I say, OK, oh, this is actually a star. What about this one? Oh, this is a galaxy. You can kind of inspect this. You can, and let's add another one. Let's basically say, let's do this one, cron. Again, I don't know what any of these actual metrics mean. I'm not an astrophysicist. But now, one of the big things they wanted to do is they say, oh, there's something interesting happening over here. Okay? What does the other metric look like? And so these are tied together. And tying them together is very simple. It's just like one line of things saying, I want these tied together. Okay, that's great. I want to look at it in a different view. So we got a detail view. And here we have kind of, these are the top is the individual vertices, the individual visits that this data comes from. And this is like a mean of it. Eventually, phase 2, they want to be able to click on this point and open up the actual entire data set that comes from that point, which we don't have implemented yet. These are all linked plots. So if I move something, if I move this, the one, yeah, of course it's not going to work now. So if I move this, the one below moves too. And then they want to know, so this is a metric. This is the Gaussian magdiff for the entire star map. And they want to be able to say, okay, actually, I'm only interested in this little area of the star map. Where do those points occur in this metric? And, yeah. Okay, I'm having problems with my mouse. You know what? Let me check something. Yep, I crashed something.
It's probably the mouse.
Yeah. Let me see if I can redo that. As I said, this is not fully stable code yet, but it's getting there. Okay. Let me get one of these and switch over to the detail view. Okay, so if I use this selection and I select a portion here, the portion of the star map I selected there is now what is being shown in this plot. Then let's go back to the sky view. These are all this data is linked. So so they've got these metric filters which are true or false. So I can say QA bad, and I think QA bad true means it was a bad point. And so if I do QA bad true and I can add that filter, it will get rid of the data where the QA flag was bad. And so I can stack these filters. You can say this one, oops, this one is false. So now I'm interactively exploring my data, adding filters to it, and it's all dynamic. One last thing I'll show, and then you can remove the filters. I'm going to remove this one. And if you had 5 or 6 diagnosis, 5 or 6 metrics open, these filters would be applied to all of them. Let's see, remove. And this is the one that actually we showed this at they had a users meeting. And we kind of showed a demo of this, or we were going to, and the folks at Princeton basically said, can you do this? And we're like, well, we haven't tried it, but we can just throw it in and see if it works. But they had these 2 metrics, and they said, can we have a arbitrary query that we run on the data? And we're like, okay, let's try it and see if it works. And what was the other one? It was this one. If they said, no, one is, I think, flux. And this is for power users. If they wanted to say this metric divided by this other metric, is greater than 100. And this is just passed into the pandas.filter expression. And if you run the query expression, then it should filter out the things that meet that. And they kind of said, doing this one thing, this flux by the flux error greater than 100, actually takes them a lot of time. Because they have to go back and find the data, and they have to, work out which one to use. So there's some nice functionality. There's a few rough cases here and there which we have to still fix. We can do about a ½ terabyte, a terabyte pretty well. We need to scale it bigger because right now we're using Dask on one end of the thing. We're not using it on the other end. But the thing is, this framework's now there. A lot of the features, we learned a lot through this process. There's some new templating stuff, which is going back into panel. And the next version of panel is going to have some default templates, one of them which is based on this. Getting it set up the first time was a little bit complicated because we had to understand how all the pieces work together. But if the engineers or scientists want to throw in a new plot, want to change the way these plots work, it's very easy for them to do that now. There's still some data engineering questions on how we go on really big data sets, but this enables continued innovation. Whereas if we built a custom application using JavaScript, D3, all the latest JavaScript tools, we'd have an amazingly slick app, and some of the kind of things which were a little clunky here might not be there, but they would have no way to move it forward without paying someone else to do it. And so that's a large part of the motivation in this. And I'm going to end with two things. I'll take questions, but I wanted to really shout out to the open source community, because the HoloViz team, there's, I think John Luke is here, and one of his other, Philip, he helped us because we kind of stressed panel and stressed HoloViews with data sizes and features that, this is one of the more complicated apps, production apps built on panel. And so we found bugs and he fixed them amazingly. So this was, and Brendan's at the back as well. He wrote a lot of I did a lot of the back-end data stuff. Brendan did a lot of the front-end panels and other HoloView stuff. But this really was domain expertise and plotting expertise from Tim, because I do not know how to detect whether something is a galaxy or a star, that whole algorithm's Tim's. We were paid as Quantsite to try and work out all the different pieces, and the open source community really helped us where we found things and we were able to fix some bugs, they were able to fix some bugs, but finally we have something that the LSST should be able to take forward and use on their data. And I'm pretty excited, 10 years of surveys on the night sky, that I think folks are going to learn a lot from that. So overall, this is one of those projects where it was fun from a technical point of view, but it's also fun. You're like, oh, we're working with the LSST telescope. That's also a fun part. So I've got some links here. All the code for this is on GitHub. It's not perfect. There are, you can see where we have put hacks in that we haven't fixed. I have 2 publicly available data. All the data is actually going to be publicly available. It's just huge. So I have 2 data sets that you can use with the dashboard. One is a 1% data set, which is about 7 gig. No, I think I have a 1% and 10% data set, and they're 5 gig and 20 gig or something. The whole test data set is about 70 gig or something. So I haven't put that online yet. So if you want to play with this, try it out. It's a little buggy. You can hit corner cases, but you can always email me. Also, just to plug Quantsite, if you need to do something like this and want our help, we're happy to help too. And we'll do it in a way where you can take over. So I'm also happy to take questions now. Thanks. Right now, I think all the plots are data shaded. The one caveat is in some of them, so ideally we should be using Dask directly with data shaded plots, but because we kind of had some time crunch issues, in some places we did a dot compute before giving the plot to HoloView/data shader. So because of that, we're kind of we have an upper limit on right now. Certain data sets have to fit in memory to work, but that's an easy fix. We just haven't got to it. But yes, they're pretty much all data shaded.
Are you thinking incorporating other components locally into the environment? Is that
so panel supports Plotly plots. In this particular project, I don't see any need to. The last time I had to work on something, the main thing that Plotly had, which I couldn't find in HoloViews, this was like 2 years ago or something, was 3D plots. But then afterwards, someone built a VTK.js plugin for panel, so I did the 3D plots with VTK.js. So you can, if there's a Plotly plot that you really want, panel can integrate that, and so you can actually have a Plotly plot and a matplotlib and different things in the same dashboard very easily. Right now, HoloViews does everything we need for this project, so in this project, not really. Yeah. Any other questions? Okay, so I'll be around for a little longer, and the code's up, and feel free to email me. Thank you.